In this lecture, we will see the operation of a push-pull converter. So push-pull is again a DC-DC buck-derived isolated DC-DC converter. So the difference between forward converter, so this is the tertiary winding based forward converter for regeneration, and this circuitry is nothing but a forward converter. So a forward converter, this converter is called as a forward converter because it operates only in the region 1 or in the only one quadrant of BH curve. This is the BH curve. So this push-pull converter will operate in the region 1 as well as region 2. This will result in the better utilization of the transformer core and thus enhancing the efficiency of the converter. Also, what will happen is that it will also enable the power converter to operate at a higher power level because the core is utilized. The power rating of the converter will increase. Given that the transformer is almost the same, if you are utilizing both the allowable BH curve quadrants of the converter, which means that we can use the converter for a wider range of applications. So that's why a push-pull converter get its name based on its mode of operation in region 1 and 2. So H and B. Say this particular point is IM or phi m. So it operates, it starts from here, it goes here, then again comes back, goes in the negative direction, hits this point and again comes back. So between region 1 and region 2, one is called as the push region, other one is called as the pull region. Push region means the core is been magnetized, and the pull means the region 2 of operation means that the core is demagnetized. So that's why this converter get its name as push-pull converter. So then what we were doing in forward converter is that we were allowing the magnetizing current IM to rise in one direction and make it 0, again rising it and again making it 0. But here our aim is to make IM negative. This is x-axis is IM and y-axis is 1 by Lm integral VLm dt, and the slope is Lm. So in order to work the converter in this region 2, so if you just see the BH curve, IM versus this, so IM or phi m, we can say either IM or phi m, and either it is 1 by Lm integral VLm dt or MMF, because the B versus H graph, the slope is mu, and L, because we know that B is mu H. Inductance is N square by reluctance, that is L by mu A. So therefore on the X, and we know that IM is 1 by Lm integral VLm dt. So if this is x-axis, if this portion is on y-axis, then this becomes the slope m. If this is on y-axis, if this is on x-axis, then this becomes the slope n. So slope is a function of the relative permeability of the material. Mu equals to mu naught mu r. Here also n square L by mu a. So n square by reluctance, where reluctance is L by mu a. This can be written in terms of MMF also. B is mu h and B is phi by a. So phi is a mu h, and h, we know that h into L equals to Ni. So h will be Ni by L. So will be a into mu into h, which is Ni by L. So L by mu, that is reluctance. So Ni is MMF by reluctance. So again, this has to be y equals to mx. So flux has to be on y-axis. this has to be on y-axis and mmf has to be on the x-axis. Then this slope becomes reluctance, 1 by reluctance, that is L by mu a, that is mu a by L, because the slope should have the mu term. And L is directly proportional to mu, so that's why we Im is here, Im is on x-axis, so either it is so phi should go on y-axis and x on axis should be mmf. So I think I reversed it here. Either it is b versus h graph, or it is 1 by lm integral Vm of dt versus Im graph, or it is on y-axis, what should be the term? Phi. Either it should be phi m or what? mmf, magnetomotive force. So in order to operate in both the regions, so here in forward we used one switch. So with one switch it is very difficult to operate the converter and to change the direction of Im. So operating in this region means changing the direction of Im. Changing the direction of Im. Im is on x-axis, so x should be negative. X and y both should be negative. It means that if the negative current flows through it, it is magnetized in the other direction. Quadrant number 2 and 4 has no physical significance. It means that if Im is negative, B is positive. It means that when you are removing energy from the inductor, it is getting magnetized, which is not the case. Or Im positive and B negative means if you are energizing the inductor with a positive Im current, it is getting magnetized in the opposite direction, or it should be it will provide energy. Basically, that is the thing. So the product of B into H should be positive always. That's why we should use multiple switches. So that's why once we are exciting the winding in one direction, and in the other case we are removing the magnetization of the winding using the other switch. So we can take the help. And also in primary there is only one winding, so even if you put two switches, combination of two switches, we are unable to magnetize and demagnetize the single primary winding. That's why we should have multiple primary windings, or instead of that we can have a center tap winding. So two switches are needed for both 1 and 3 quadrants of operation of BH curve. And also we need a center tapped transformer. That's why the circuit of the push-pull converter will be like this. So first I will draw the transformer. First we'll draw the primary. We are not bothered about the secondary. This is NP is to NS. So this is the dot convention and this is the dot convention for the windings. So what we'll have to do is, with the center tap we'll get two sets of primary windings. So we'll use two switches in a complementary fashion, just like in a synchronous DC-DC converter, where in one case for switching off one switch, the upper set of center tap winding is magnetized and the other one is demagnetized. Or we are magnetizing one set of primary windings at a time. That should be given. So we have to have a source B in, . like this. If we connect it here, so once this terminal should be connected here, and once this terminal should be connected here, so it gives the possibility of two switches like this. This we'll call it as S1, this is S2. So this terminal is called, this is ground 1 and this is ground 2 because it is an isolated converter. The secondary can be a any converter with a diode, and basically it is a buck derived, so output section will be LC. And this is R, LC. This is again G2. So the secondary is a box. So the box can have two configurations. Configuration 1 and configuration 2, because it is a buck derived. So either it can be like this, secondary can be like this. Second is also center tap. Say that the second is center tap. So this is based on the switching. So here if S1 and S2, so there can be, as there are two switches, there can be 4 modes of operation: on off, off on, off off, and on on. So when it is on and off, it means when S1 and S2 are alternately on and off, it means that either the upper set of winding is powered, the lower set is not powered, or vice versa. If it is off off, it means that no set of winding is powered. So basically primary side there is nothing. So in the secondary side, basically the inductor will freewheel. And when it is on, what happens is that the primary winding is short circuited. So the primary is short circuited. So what will happen if the primary is short circuited? The secondary will be short circuited. So it means that you are short circuiting this ends. So typically it is not allowed. Why? Because so if the dot convention is like this, what will happen is that when the switches are on, say when S1, S2 are both on, the primary will be like this. It will be like this. This is dot convention, this is dot convention, this is V in. So the V in will appear here, minus plus, and this voltage and basically this voltage is 0. So minus plus, so it should be plus minus V in. For the overall voltage in this loop to be 0, this has to be the case. It means that if this happens, the common point of it, so basically this is a dot convention and here it is a negative is there. It means that the core is magnetizing as well as demagnetizing, and it's a short circuit, means IM will be freewheeling. IM will be freewheeling through this path only. So IM is freewheeling, which means that the core is demagnetized. The below core Vin is supplied with a voltage of Vin. So the problem here is due to the dot convention. A center tap, basically what happens is this turns is NP by 2 and the turn here is NP by 2 because the overall primary turns is NP. So center tap transformer only assures that voltages of equal polarity are being induced across the center taps or the center tap windings. If you short circuit or if you turn on both the switches, due to the dot convention, the voltage induced across the upper set of winding does not obey the dot convention. Also, it is you are short circuiting the complete primary winding, which means that IM will be reducing to falling to 0. The core is not demagnetized. So and below thing you are applying Vin. So means you are pumping energy into the inductor and again removing the energy from the inductor simultaneously. So this is not allowed. So this condition is invalid. Due to dot convention. Due to dot convention, what happened? Unequal voltages are not unequal voltages due to the dot convention, directly due to the dot convention, and the core is magnetized and demagnetized simultaneously. So that's why this condition where both S1 and S2 are on is invalid. So secondary side what we can have is either we can have two diodes, then we need to have the inductor like this and the R. Then how to connect it? So it's as a secondary center type. So this is, let's say this is plus minus, this is plus minus. So what happens is the common terminal here should be taken as the ground, as a new ground. Just like say we have a 30 volt supply and if we want to get a plus minus 15 volt supply, so say this is 30 volt minus plus. So we have a resistors and we have split capacitors, and say that this is the new ground which we take. So what will be these voltages? This is C, this is C, this is R, this is R. So even if we don't use the resistances, the capacitors will try to maintain the voltage across them, but they may fail to maintain equal voltage across each of them. So that's why these capacitors, equal value of capacitors, are used to what? This is plus minus, this is plus minus, and say that this is the polarity of the electrolytic capacitor. These resistors are used to split the voltage. It means basically some capacitor may be overcharged, some capacitor may be undercharged. So charging, and if the balance is not there, the voltages across these capacitors will not be equal. So these resistors are used as a passive elements to maintain the charge balance across these two capacitors. So let's say this is 30 volt. So this should be plus minus and plus minus. So what happens is, if we ground this port, then what happens is this is 15, this becomes ground, and with respect to ground, this is at the lower potential. So this terminal becomes plus 15 and this terminal becomes minus 15 volts if you ground this. So by using this principle, if we take the common port, so because say whatever is the, say this is Vs by 2 and this is Vs by 2, because the overall secondary voltage drop is Vs, say that so this is the turns ratio is NP by 2, NS by 2, NS by 2, equal turns ratio for the secondary winding. So this ground and this ground is there. you have to connect it as it is. So what happens is this terminal becomes positive polarity and this terminal becomes a negative polarity. Now you have to connect a diode. How will you connect diode is, you can either connect two diodes like this, or what you can do is you can short circuit both of them and connect a diode just before the inductor here, somewhere here. But what happens is, if you split the diode, the voltage drop across diode can be this thing. So if you directly short circuit the secondary winding, so if you use diode here just before the inductance and directly short circuit the secondary top and the two end leads of this secondary winding, it results in short circuit of the secondary winding. So it's better if we split the diode into two halves and put one in each of the paths, and then you short circuit it and connect it to the source. So this is the configuration where the secondary itself is a center tap. Then configuration 2, we can take help from the what? Say this is NS and this is VS. We have like this. And this we can use as a full bridge diode. With this as what? G2. Sorry, G2. So configuration 1, in configuration 1 there is a center tap even at the secondary. In configuration 2 there is no center tap at the secondary. Directly we have a full bridge diode and then it is rectified using 4 diodes. The only thing is that the requirement of the diodes is increased. But the plus point in configuration 2 is that we don't need a center tap. So if we don't need a center tap, then it is advantageous because there is no need to equally split the number of turns, so that equal voltage should be distributed, just like this circuitry from 30 volt to plus minus 15 volt. So these are the two configurations. So we'll analyze the circuit using configuration 1 to analyze the steady state operation of the push-pull converter. Now to study the steady state operation of push-pull converter, we have to see the magnetizing path and how it is. So then we see the magnetizing inductance path. Is basically path. So basically we have to see LM and IM, how they are split. So if you have to analyze the magnetizing inductance path, so first we have to see the operation of a center tap transformer, that how a center tap transformer will behave. So as we are taking configuration 1, I am drawing secondary also as center tap. This is NP by 2, this is again NP by 2, NS by 2, and this is NS by 2. So as of now, this ground path I am not connecting, I am just keeping it open. So so we basically have to connect this ground path. So I am erasing it from here. So first, then we'll see the operation of a center tap transformer. Operation of a center tapped transformer. See that we have this center tap transformer where both the primary and secondary are center tap. This is the dot convention, this is the dot convention, here is the dot, and here is the dot. Say that we excite only the below winding as V1. So what will happen is this voltage V1 will come here. So what happens is that, so here what happens is, even if we excite this, the lower bottom winding V1, so the voltages induced will be, so say this is NS overall, this is NP. So this will be what? V across first to V across second is number of turns across first divided by number of turns across second. So now we want to find V2. So V2 will be V1 into N2 by N1. So for it, this will be what? V1 into number of turns of this winding into NS by 2 divided by what? Number of turns of the NS by 2 winding. So same voltage V1 will be induced across the upper primary winding. So overall this voltage 2V1 is induced. So here the voltage which is to be induced here is 2V1 into N2, that is NP divided by NS overall. Then based on the number of turns, if you want to see voltage, what is the voltage induced across this winding, so we have to see this. So there are 4 windings: winding number 1, winding number 2, number 3, and number 4. Only one is the source. So what will be right is V2 will be, this is V2. For 2, this is V2. What is V2? Is V1 N2, that is NS by 2 divided by N1, that is NS by 2. For 1, what is the voltage V1? That is V1. And what is the number of turns? NP, sorry, that is NP by 2, not NS. NP by 2 divided by NP by 2. So we let NP by 2 and here NP by 2, and this will get cancelled. This will be V1. Voltage induced across the third winding, that is V3, will be V1 into number of turns across 3. V3, what is V3? This is N, have interchange primary and secondary. This is NP and this is NS. So V1 into NS by 2 divided by NP by 2. So divided by 2 will get cancelled. It will be V1 into NS by NP. Similarly, the voltage induced across the fourth winding, before is what? V1 into NS by 2 divided by NP by 2. 2 will get cancelled. It will be V1 NS by NP. And the overall secondary voltage will be V3 plus V4. That is 2V1 into NS by NP. So here we have verified both the laws. So V1 NS by NP, NS by NP, and this is V1 NS by NP. So based on the number of turns, we have verified that what should be the voltage drop across each of the windings, and also by using the KVL, the means as the number of turns are same, so half of voltage will be induced. So it means that if either any one of the winding is so say that in primary side, if one winding is powered, the same voltage appears across the upper or the other set of primary winding itself. And at secondary individual windings, the voltage induced is V1 into Ns by Np. So this we should keep in mind. This is the working principle of the transformer. Sorry, of a center tap transformer. Then we have to show the magnetizing path. So in order to represent it, we are magnetizing 1 as the magnetizing branch. We are showing the 1 as the magnetizing branch. So Lm should be here, should be placed here. So basically what I'm trying to say is that this is Lm, this is Im. And this is the primary set current I1, this is I1 dash. So this is how the magnetizing branch is shown for a push-pull converter or for a center tap transformer. So now we'll see the steady state operation of this converter. There are two switches, 0001, 1011. We already saw that 11 is not valid because the dot, as per the dot, we will see here, we saw that the overall voltage, the overall primary winding is short circuited. If Vn is applied here, the voltage induced across the upper primary winding will be Vn into N2 by N1, but the dot polarity sign convention is reversed. And also at the same time, as it is short circuited, the overall voltage in this path should be 0 for Im to free wheel, so which is violating both the principle. So 11 we are not take into consideration, which means that both the switches cannot be turned on simultaneously because of the dot convention. If our dot convention was different, then it would have been possible. So any switching state, any possible switching state does not mean that it is a useful switching state. So, but in our case, we are not using it. Now, once we start analyzing this circuit, you'll understand and you'll appreciate why the dots are kept like this. So, let's draw the switching pulses of the push-pull converter. Say that this is for switch S1, this is for switch S2. This is one switching period. This is T switching. Like this. So we know that both the switches can't be turned on simultaneously. So what we do is, in order to have effective, so for Lm, for if you want to plot phi m, first we'll plot phi m. So the switching pulses again, I will draw like this. It is like this. Till here is the switching period. So, and this is half of the switching period. Means this portion is T switching by 2. This portion is T switching. T switching. So the switching frequency for both the switches are same. And what we do is, so phi m in our forward converter was like this. it was only going up, becoming 0 before turn on of the next cycle. So our aim is to now bring this IM in the negative quadrant also. So which will happen when S2 will be turned on, when either of the switches will be turned on. So say this is S1 and this is S2. So say here we are drawing phi-m or IM. So how will it look? So initially this thing, first we have to see what will be the phi-m and IM when both the switches are turned off. So say if both the switches are turned off, how will be the magnetizing current phi-m? So say this is the converter. So both the switches are turned on. There is no current flowing through this branch. Both are open. So how will be the IM? So there will be no change in the flux in the transformer. The flux will be constant. So whenever both the switches are off, the flux will not be rising or falling. It will be constant for some time. So during this time, so when S1 is on, what happens is when S1 is on, S1 is this switch. When S1 is on, this Vin gets connected between the lower switch. So this Vin comes across this end. Here it means that if Vin is directly connected to the LM branch, it means that IM will increase because Vin is almost constant. So we'll say some rising edge. We'll show some rising, that we don't know what is the initial value of it. Say it is some rising like this. Then what happens is, say that till this time S2 is not switched on. So if we switch S2 in such a way that the overall waveform is symmetric across positive and negative edge, because that is our ultimate aim. So then the requirement for that is that S2 should be turned on after half switching cycle only. So here I'll draw like this. Yeah, this is again another cycle. This is the second switching period, and this is again half of this switching. This is again half of this switching period. So again this will be on and it may turn off like this. So when, in order to have symmetry, the switching pulse of S2 should start after half of the switching time. So for both the switches, the switching frequency is same. It's not that different because both switches are controlled using the same PWM pulses. So when both the switches are off, the phi-m is almost constant. When the S2 switch is on and S1 is off, what happens is the Vin gets disconnected from here and it gets connected here with plus polarity here. Wait, I will show you the polarity. When S2 is on, negative terminal gets connected to the upper end. Okay, the dot end, it will get connected to the dot end. So the polarity here I have reversed. So here, yeah, negative will be here and positive will be here, which means that if this switch is, if the upper left winding is powered, we have to shift this magnetizing branch to the upper end like this. This is LM and this is IM. because now the lower bottom winding is not powered. In this case, what you have seen that the voltage across the LM winding is of reverse polarity of that of the dot convention. So here the voltage which will be induced across the below primary winding will be V in, where negative is here and positive is here. It means that a negative voltage is applied across this LM branch. The LM branch always should be of this polarity. It will not change its connection. Why? Because the dot polarity is here. So this is I1 current and this is I1 dash current. Now this is I1 current and this is I1 dash current, like this. So now the core is demagnetized. So with the same slope it will fall. So, and it goes in the other direction. It should go to the other direction. So typically it should be like this. Then again both the switches are off. So it will be like this. Then again till here, what happens is it should turn on like this. It should turn on like this. Again when both the switches are off, it should be constant. So this is phi m comma Im. Now initially what we thought is that this is Im of 0 or phi m of 0 or phi m of 0, whatever it is. To have a symmetric waveform, we can start this waveform from this point only, like this. So at the end of each switching period, the value of Im of 0 is equals to the value of this. So I'll draw the whole waveform. Phi m comma Im. Again it will fall here and again it will rise to the same slope. This is a straight line. So this Im waveform is a symmetric waveform now, with its average value as 0. It's not a compulsory thing for a transformer to have its average value of Im as 0. Why? Because in forward converter the average value is non-zero. The waveform of Im is like this. Its average value is not 0, but it's a mandatory requirement for the transformer that if in one case the core is magnetized, in the other case the core should be demagnetized, either in the same direction or in the opposite direction, which means that it can operate either in first quadrant of BH curve or in the third quadrant of BH curve. Here you can see that Bm and Im are positive and negative, which means that it operates in both the available quadrants. So based on the nature of symmetric waveform of Im, so that whatever is the value, whatever is the rate of magnetizing the core during the turn off of one switch, it should be very much equal to or symmetric across the turning on of the other switch. That was the requirement. So based on this requirement, what we saw is that the switch S2 should be turned on, or you can say that the switching action of the switch S2 should be delayed with respect to S1 with a time period of T switching by 2. Because you saw here that after T switching by 2, if S2 switching action turns on, then the waveform is very symmetric. So that was my aim to say and to separately draw this waveform again, because there can be multiple combination of switching combination of S1 versus S2, and in these cases you see that S1 and S2 are not on simultaneously. So if this is the T on time, and this is again the same T on time, it's that the switching of S1 and S2 is same, only the difference is that it is delayed by some time. So D on is this is T on, so T on is D into T switching. But in this case we have to make sure that S1 and S2 should not be turned on simultaneously. So it is fixed that S1 will be turning on after T switching by 2, which means that this T on, the maximum value of T on can be T switching by 2. So T on max should be less than equals to T switching by 2, that is D into T switching. which means that D should be less than equals to 0.5 or half. This is the requirement of a push-pull converter. So in a push-pull converter, we cannot operate the push-pull converter with a duty ratio greater than 0.5. That is the requirement. So in this case, till now we were in a position to draw the steady state waveforms of any DC-DC converter, starting from buck converter to forward converter. In this case, it will be a little bit challenging to visualize and draw the waveform. So it is better if I select the configuration 1 and if I draw the voltage, and if I draw the circuit configuration during turn on and turn off of both the devices. So basically there are three conditions: S1 on, S2 off, S1, S2 both off, and S1 off, S2 on. So these three, and again the last stage is S1 off, S2 off. So basically in a switching period there are 4 types of switching. This is of S1 and this is of S2. So switching, there are 4 types of switching condition. This is 1, this is 2, this is 3, and this is 4. 2 and 4 are the same. So basically there are 3 identical conditions. So we'll draw equivalent circuit of the push-pull converter. First, case 1, S1 is on and S2 is off. How will the converter look? In this case, what will happen is that this is V in, this is plus, this is minus. So this is on. I'm directly short circuiting it. This is S1 and this is S2. This is off. So as the lower bottom, as the lower or the bottom side of the primary winding is powered, we'll place the LM branch here. This is the LM branch. This is the IM current. This is the, so as the switch is on, the current here it is IS1. So this current, same current will flow here. IS1 equals to I1, this current I1, and this is the reflected current of the I2 dash, overall reflected current due to the secondary windings. So here this is V in, the voltage induced here is V in, with plus here and minus here. Similarly, as per the dot convention, V in voltage is induced here, plus and minus. If we write Vs2 minus of plus, Vs2 will be equals to V in, because S2 switch is turned off. So what happens is, the voltage induced across the secondary will be what? V in into Ns by 2 divided by Np by 2. So by 2 will get cancelled, and similarly this will be plus, this will be minus. So this will be V in Ns by Np. This is plus, this is minus. Then we have the diodes. I told you the reason why we are using diode and then short circuiting and then using this inductor is because otherwise the secondary will be directly short circuited over a secondary winding. and this is the load. This is IC, this is IL, this is VL, this is V0, this is C, this is L. This is, say, what was the diode? I think I did not name the diode. Okay, so let me write the name here. This diode is D3, this diode is D4. So D3, D4. This is ID3, ID4. This is VD3 plus minus, and this is VD4 plus minus. So I think this is the equivalent circuit of the diode. So basically, I am using the green color for this thing, that it is turned on. So this is turned on. So as positive terminal of in the secondary, positive terminal is connected here, so it will be on, and here this will be turned off. Similarly, this is turned off, this is turned off. This is off, and this means that the device is on, or I can write like this: on, off. Okay, so what happens is, during when S1 is on, this core is getting magnetized because plus V current is flowing through here. So we'll write the values of each of the parameters, and so what is VS1? What is the VS1 is 0. What is IS1? So if this is I2 dash, this will be I2 dash by 2, and this current will be I2 dash by 2. So why I2 dash is because so this current will be ID3 will be what? IL current to flow here, and this current will be 0. So basically what happens is that so let's say that both the diodes are turning on simultaneously. So in that case, whatever is the overall current across this secondary, the overall reflected current should be observed here across the individual branches. Okay, so in this case, as this current is 0, so this reflected current is I2 dash will be this. This is, so okay, we'll name each. Let's say this is winding 1, this is winding 2, this is winding 3, and this is winding 4. So I'll write it as I4. This is I3. So I3 here is IL. So this is I3 dash, and this will be I4 dash. I4 dash will be, I4 dash is I4, which is 0, and I3 dash will be what? I3 into, so for transferring the current, so first we'll write the relation V1 by VI, we'll write I for the ith winding is equals to N1. What is N1? That is Ns by 2 divided by Ni, which is equals to the current. Now the current, the inverse relation should be followed. that is I by I1. Now say everything is referred to primary side, so we'll let here I dash and I1 dash. So therefore Vi will be what? V1 into Ni by Ns by 2, and I1 dash, we have to write I1 dash or I dash. So here what we can write is I4 by I4 dash is Np by 2 divided by Ns by 2, which is still Ns by 2 divided by Np by 2, because it is the reverse relation, which is still 0. So here I3 dash will be what? I3 dash is I3 into turns. So basically the relation between turns and current will be reverse. So V1 by V2 is N1 by N2 is I2 by I1. So I2 is I1 into N1 by N2. And if you want to transfer the current, the reverse relation should come. So we don't know I dash, so we can write I dash is I1 dash into Ns by 2 divided by Ni. Again I did a mistake, it should be Np. Because it's a primary winding. Okay, so it should be like this, I1 dash, and it is, yeah, so by 2 will get cancelled, so it will be Np by Ns, Np by Ns, this current will be Np by Ns. This is the I3 dash, and I4 dash is 0. So here in this case I1, IS1 will be I1, this IS1 current will be equals to the I1 current, that is the source current, so which is nothing but, so instead of having too many notations, we will write like this. So this current, as per KVL, this current is equals to this I4 dash plus I3 dash, I1 dash, yeah. So I1, which is I1 dash, which is what? I4 dash plus I3 dash. Therefore IS1 is I1 dash, which is equals to what? I3. What is I3 in this case? IL. So IL Np by Ns. This is the current through the switch. So switch is done. Now switch 1 is done. Now switch for S1. Yeah, VS1 is done, IS1 is done. Now for S2. What is VS2? VS2. What is the voltage across the S2? If you apply KVL, it will be plus is here, plus is here. So it is Vn plus Vn, 2 Vn. And what is IS2? IS2 will be 0 because the switch is turned off. So for S2 is done, for S1 is done, for S2 is done. Current and voltage across the first and second switch is done. Source current is done. Now IM will be rising, you know already, because we have already done the waveform for IM and phi-m. So IM phi-m we are not drawing. I1 dash is also we have written. Now we'll go to the secondary side. So for D3, VD3 will be 0, that is the voltage across the diode. ID3 will be IL. For diode D4, VD4 will be what? So plus minus, so voltage will be added up. So voltage across this diode will be what? Minus 2 V in NP by NS. Minus 2 V in NP by NS. And the current through this diode will be 0 because it is reverse bias. And in this case IL is rising. We already know that the same assumption holds, that this inductance L is sufficiently high so that the this converter operates in the continuous mode of operation. So this is done. I4 is 0, I3 is IL, I3 is ID3, which is already written here, IL, and I4 is ID4, which is 0. Everything is written. I think nothing is remaining. Then we'll go to case 2. Case 2 is when S1 is off, S2 is also off. Yes, so this is S1, this is S2, this is V in plus minus, and in this case, so the magnetizing branch can be kept anywhere. So say that this is the magnetizing branch LM, this is IM, this is the dot convention. So in this case what happens is that, so in this case if we draw the secondary, so in this case what happens is, we saw that say IM has reached some value before turning off of both the switches. So we saw that IM stays over there, so the current IM does not increase or decrease. So in the circuit configuration, what happens is that as both the switches are turned on, no voltage is induced across the primary. There is no voltage across the primary. So basically what happens is, this voltage becomes, this is 0 volt. With this polarity, here it is 0 volt. With this polarity, so similarly this is again 0 and this is 0. Plus minus plus. So basically there is no polarity in 0. So the diode, this diode D3 will be turned off, or it will be reverse bias. Similarly this diode will be turned off. This switch is turned off, this switch is turned off. Everything is turned off in this case. So what happens is, this now there is a problem here. There is no way for this inductor current to freewheel. So we added diode like this to freewheel. This is diode D5. So this diode D5 will force turn on this particular circuit. This will be turned on. So even if you don't place this diode, what happens is that this inductor current which appears here, say there is no diode D5, it will go across this branch, it will go up like this, and it will be splitted as IL by 2 and here as IL by 2, and it will force turn on this MOSFETs if we don't have this particular device. So this I am denoting by red color. Say that you don't have D5. So this inductor current will be split into half. IL by 2 will flow through the upper diode and IL by 2 will flow through the lower diode. So it will force turn on this diode D3 D4 irrespective if there is no induced voltage across their terminal. So if this is if there is some current here, say that we are not using D5, we are just using D3 and D4. So here what is the current induced? Say this is IL and this is I switch. So IS1 is IL and IS2 is 0 because the switch is turned off. So IS1 is an IL, IS1 which is IL, or I1, not IL, it is I1. I1 is 0. So what happens is here some current is induced, that is IL by 2 into what? NP by NS. Similarly here IL by 2 NP by NS. This current will flow. So what happens is, as current after this branch there is no path to flow, so this current IM will be equals to minus IN by 2. So this current IM will be equals to minus IL by 2 into NP by NS if there is no D5. If there is no D5. So for S1 what happens is IS1 will be 0, but what will be the VS1? So there is no voltage induced, so VS1 will be 0. Similarly for S2, IS2 equals to VS2 equals to 0. So I1 will be IS1 which is equals to 0. And so here what happens is this current should be induced here, but as this switch is turned off, this current should be ideally equals to 0. So which is a problematic term. So here what happens is that we saw that even if we don't use D5, there is a path for this IL to freewheel, that will freewheel to D3 and D4. So as based on using the transformer basic principle, if we see the reflected component of the secondary through the primary, we saw that this IL by 2 current flows through both the center type windings. So both these windings should have current induced, but the current in the upper branch should be 0. Why? Because S2 is turned off, so which is not a valid case. So but IS2 is 0, so therefore IL by 2 NP by NS should be 0, which is not valid. So we need the diode D5. So I'll remove this term. We need this term. So what happens is, I will again erase this and write here 0 current flowing. this will be 0, I will be 0. So here I will be 0. And here this I will be 0. So basically what happens is, as there is no current here, there is no path for this IM to fall. So IM is constant momentarily. So therefore IM is constant, as there is no path to flow. So in that case, what happens is VD3 equals to VD4 equals to what? 0, which is equals to Vs. Why? Because those are connected in parallel. I mean, in series. So what happens is, so basically it is like this. Say it is Vs. Vs equals to so if you just apply KVL in this loop, minus plus, plus minus, and minus plus. So Vs plus Vd4 equals to Vd3, but Vs is 0. So therefore Vd3 equals to Vd4. But as it is reverse bias, the voltage is 0. So, and also the currents, IS3 equals to IS4 equals to 0. So the ID5 will be equals to IL. ID5. So the current is continuous. And the last case is when S1 is off and S2 is on. So now we'll see the operation of the push-pull converter in the three modes. When S1 is on, S2 is off, it's complementary action, and when S1, S2 both are off. So here I have drawn the waveforms of S1 and S2. Here you can see that instantaneously S1 is on, S2 is off, then S1, S2 both are off, then S2 is on, S1 is still off, and then again both are off, and then this cycle keeps on repeating. And we have already discussed that S1 and S2 can't be turned on simultaneously. So just a quick overview. So we'll see the first case. So in order to draw the steady state waveform of the push-pull converter, we'll first see the analysis of the circuits in these three conditions. So there are three separate individual conditions. So first case is S1 is on and S2 is off. So here you can see, so also how the magnetizing branch is split in a standard wave transformer is that the LM branch is split as LM1 and LM2, where LM1 and LM2 are split proportionally with the proportion of the primary turns. So as in this case it is equals to, so LM1 and LM2, which you can see here, is LM by 2, overall LM by 2. So when S1 is on, the Vin is connected across the bottom primary, or here you can see the one number winding, the below primary is below winding. So the end S2, so basically the above winding, S2 is off. So the voltage across VS2 when S2 is off. So what happens is, first this Vin is applied across the bottom primary, so Vin is seen here. So similarly, corresponding to 1, the voltage induced at the fourth winding is Vin into Ns by Np. Similarly, across 3 is Vin into Ns by Np with the dot polarity. Here dot is positive, so here also dots are positive. Similarly, if Vin is here, same Vin is induced across the above primary winding, that is the winding number 2. So that's why the voltage across the switch VS2 when the switch is open is Vin plus Vin, that is 2 Vin. And as S1 is off, voltage across S1 is 0. And so what happens is, due to this polarity, diode D4 is reverse biased, D3 is forward biased, and thus I4 is 0 and I3 is IL, that is the inductor current. So similarly, I3 dash is induced in the primary, which is I3 into Ns by Np, and I4 dash is 0. And the in this LM branch, the flow of I3 dash and I4 dash, irrespective of all the switching condition, is in this fashion. that is I3 dash. You can see it flows like this in this loop, and I4 dash flows in this fashion. So as VS2 means as the bottom as the top primary winding is not connected, so this current in this branch is 0. I equals to 0. Current here is 0. So that's why the current which goes input, the input current is whichever is going in this side should come out of this side. As this is turned off, so the current should come from this side. And as I4 dash is 0, there is no contribution of I4 dash in LM1. So therefore, what happens is, in this case, the current through the switch S1 is equals to the input current, and the current IM1 becomes I in, because I4 dash is 0. Similarly, in the top primary winding, what happens is, this current is 0. So basically whatever is the I3 dash current, that is only the IM2 current. So IM2 is I3 dash, that is I3 into NP by NS. So the overall magnetizing current branch, that is IM, that is IM1 plus IM2. So it becomes I in plus IL into NP by NS. Similarly, we can see that the currents and voltages across the different devices. So here the red is off and the green means it is on. So similarly for case 2, when both the switches are off, so there are two conditions. One is without the use of D5, one is with the use of D5. Without the use of D5, what happens is that the inductor current freewheels through both these diodes, D3 and D4. So these two diodes are forcefully turned on. So this is I3 is IL by 2, I4 is IL by 2, and thus I3 dash is NP by NS IL by 2, I4 dash is NP by NS. So this is I4 dash. I4 dash is what? NP by NS into IL by 2. This is the current. So what happens is, as both the switches are turned off, so there is no contribution of the input current. There is no input current on, so I in becomes 0. So the I4 dash and I3 dash freewheels to the magnetizing branches. So IM2 will be NP by NS into IL by 2, and I4 dash or IM1 is minus of I4 dash, that is minus of NP by NS into IL by 2. So the overall magnetizing current becomes 0, that is addition of both the things. So in this case, what happens is, the core is neither energized nor de-energized. In the first case, the overall magnetizing branch current was positive, which means that the core is magnetizing. So the magnetizing current increases. In this case, when both of the devices are off, the magnetizing current becomes 0. That is, the core is neither magnetized or demagnetized. That is, IM is constant, or phi m is constant. In the same under the same case, when D5, there is a diode D5 which is seen here. So IL, instead of freewheeling through D3 and D4, it freewheels through D5. Similarly, so I3 becomes 0, I4 becomes 0. The magnetizing current IM1, IM2 both are 0. Input current is 0. Everything is 0. So the core is not magnetized. And when D5 was absent, in that case D3 and D4 were forcefully turned on. So one component of magnetizing branch was magnetized, the other component was demagnetized simultaneously. So that's why the overall magnetization is constant. And the last case, in the last case, when S1 is on and S1 is off and S2 is on, in that case what happens is, here you can see that the above winding gets connected to input, but with the reverse polarity. So V2 is minus Vin. So if it is minus Vin, the same voltage is induced across the primary bottom winding, that is minus Vin. Similarly, across the secondary, as the dot convention is reversed, the voltage induced across winding number 3, that is the secondary top winding, is minus of NS by NP into Vin, that is equals to V4. That's why the diode D4 becomes forward bias, and thus it carries the inductor current, and ID3 or I3 becomes 0. So similarly, what happens is that ID4 or I4 equals to IL, and ID3 is 0. So I3 dash is 0 and I4 dash is NP by NS into IL, that is the reflected component. So again, if we do the similar analysis, as this device S1 is turned off, so whatever is the input current going, it has to come back in this fashion. Similarly, in all the cases, it has to be the case. This is I in and this is I in. So in this case, as S2 and S1 both are off, so there is no path for I in to come. So that's why input current is 0. So similarly, the same exercise can be done here. I in is IS1. Similarly, okay, so I in equals to IS2. This we can quickly write. So, and as S1 is turned off, so whatever is I4 dash, that goes to IM2 branch, magnetizing branch. So IM2 is minus I4 dash, that is minus NP minus into IL. Similarly, in the primary top winding, as we know that I in equals to IS2, means this current is I in. IS2 equals to I in. So that's why if we apply and I3 dash is 0. So IS2 is equals to IM1. So IM1 is I in. Then the overall magnetizing branch current, IM1 is minus of I in. So the overall magnetizing branch current is IM1 plus IM2. That is minus of I in minus of NP minus into IL. That is negative. So in this case, the core is demagnetized. And as we saw in the this thing, that this is the nature of magnetization and demagnetization of the core. So it starts with the value, initial value, which is positive or negative, and this is the, so based on this switching pattern, this is the waveform of the IM or phi M. The core is magnetized, constant, demagnetized, and demagnetized means it goes in the other direction. The IM current becomes negative, rising in the other direction. Then again it becomes constant, then it falls in the other direction and rises in the positive direction. So means it is this push-pull converter is a two-quadrant device. So that's why if we just start drawing the steady-state waveforms. So in case 2 where S1 and S2 both are off, even if we have a diode D5 or not, the waveforms will be same. Everything will means the analysis will be mostly similar. The only thing is that the diode D3, D4 are turned on and off. So only that is the change. But rest the overall analysis remains the same. So when S1 is on and so say these are the gate pulses of S1 and S2. First we'll draw the waveforms of S1. So this waveforms belong to S1, that is voltage and current. So this is, we'll write the cases. S1 is on and S2 is off. So this is case number 1. This is case number 1. This is case number 2. This is case number 3. Again case number 2. And it goes on repeating. So in case number 1, we'll see what are the voltage. So VS1 is 0. And in the case 2, VS1 is, what is the value of VS1? In the case 2, that is input is isolated from the primary, so it is 0. And in the case 3, VS1 is what? VS1 is minus of 2 V in. So here VS1 is minus of 2 V in. So 0, 0 and minus 2 V in. Case 1 0, case 2 0 and minus 2 V in. 0. Again 0, 0, minus 2 V in, 0, 0. So this is minus 2 V in. This waveform belongs to VS1. The other waveform, if we draw for IS1, in the first case, IS1 is what? I in. In the second case, IS1 is 0. In the third case, is1 is 0. So we should know the waveform or the nature of I in. Okay. So here we have to represent the input current I in terms of known parameters. So here we have already done the analysis of the IM current or phi m. So we'll see IM. It is the overall magnetizing current in terms of overall magnetizing current. So this is the waveform of IM. So we'll take the reference of IM and then we'll get the relation between the input current or the switch current. So in case number 1, IM was positive or it was rising. IM was rising. So in case 1, the overall IM was this. This is the overall IM. And IS1. So if we draw the overall transformer equivalent circuit, so we can draw it as like this. So our task is to bring a relation between the input current and the known currents. So the known currents, we can say that in the analysis we did till now was the inductor current waveform, the nature of inductor current waveform. So we know IL and we need one more current, and so that will take as IM. This is the IM current. This is the waveform of the IM current, and we can draw the waveform of the inductor current also. So we'll assume that there is an overall magnetizing, because we have the overall magnetizing current. So let's say that we have the overall magnetizing branch LM. So this is LM and this is the overall reflected component I say secondary dash, and this is the I input current, which is equals to the, this is V in. So this was overall IM. So now what is the I input current in this case? That is IM plus IS dash. So in this case, how we'll write IS dash, that is the overall reflected current from the secondary. This is equals to what? So as per this waveform, means as per this analysis, this was a I4 dash and this is I3 dash. So this is the overall IS dash. That is the overall reflected component of the secondary current to the primary side, as if it was not a center tap transformer. So in this case, IS dash is I3 dash plus I4 dash. So IS dash is I3 dash plus I4 dash. So here we'll write, this becomes what? We'll just write it like this. So I in becomes I overall IM plus I3 dash plus I4 dash. So I4 dash is 0 and I3 dash is I3 into NP minus, or IL into NP by NS. So this is IL into NP by NS. Because we know the waveform nature of IL, and we know the also the waveform nature of IM, so overall IM, so that's why we are denoting IN in this fashion. Then similar analysis we can do in these cases. So here IN is 0, so that's not a concern. Here even the switches are off, that's not a concern. IN is 0. So here overall we'll just copy paste, or instead of copy pasting, or okay, I will write it again. So let's assume that we have a normal transformer. This is the IN, this is the overall magnetizing branch, and this is the overall reflected component of the secondary I2 or IS dash, and this is LM and this is IM. So in this case, IN is IM plus IS dash. So overall IM in this case is basically the waveform. Based on the waveform we'll decide, plus IS dash. So IS dash is I3 dash plus I4 dash. So in this case it is what? I3 dash plus, so I3 dash is 0 and I4 dash is this thing. But I4 dash here is opposing this thing, so here we'll write the I4 dash, so basically the IM2 as in this fashion, that is I3 dash is 0 and I4 dash is, we'll write as minus because it is demagnetizing the core into S into IL. So this is the value of IL in this case. So here what I will do is, instead of drawing this waveform, I'll erase the waveform and I'll draw the waveform in terms of the known parameters first. So then it will be like this. First I'll do the waveform of 5M. Okay. I'll do the waveform of 5M. So in first case it is like this. Then it falls. Case 3, then again constant. Again rises. Constant. Falls. Constant, and again rises. This waveform belongs to IM. The other waveform is of IL. The slope of this IM waveform gives the LM, overall LM. So in case 1, basically what happens is, so basically the inductor current is, so when one switch is on, the inductor current is taken by one diode, and when the switch is off, the inductor current is taken by the other diode. So basically here the inductor current we can write as some average value. So basically, as it's a buck derived DC-DC converter, now we are referring to only output side. We know that what is the waveform of IL. So here the waveform of IL will be also similar to the analysis which we did before. So this is the nature of IL. It rises. So here we'll see that the this secondary, so the voltage across, so in case number 1, the voltage across this was V into NS by NP. So the inductor current will rise in case 1. In second case, there will be no change of inductor current. With and without diode. And in the third case, the voltage is negative voltage applied across it, so the inductor current will fall. So in case 1 it will rise, in case 3 it will fall. So in case 1 it will rise like this. Here it is constant, and it will fall. Then again it will be constant, rise, constant, fall, constant. So this is the average value of IL. This is capital IL, and this waveform belongs to IL. Similarly, we can draw the waveform of VL also. When the switch is on, the voltage across the inductor is, this is overall V in dash, so we'll call the voltage across this diode diff as V in dash. V in dash minus V naught in all the cases. In first case, V in dash is V in into NS by NP. In second case, it is 0, and in third case, it is minus of NS by NP into V in. Yes, so it is this negative, and again positive, negative, positive. In case 2, it is what? Sorry, in case 1 it is V in into NS by NP. As it's a buck converter, this is greater than this, so it is positive. In second case, it is 0 minus of V naught, so basically minus V naught. In third case, it is what? It is, sorry, this is the third case. It is minus of NS by NP into V in. minus V naught. So minus of the case 1 what we saw. So like this, it will be like this. And this is one switching period. This value is minus ns by np into v in plus v naught. So minus is to the whole bracket. This value is ns by np into v in plus v naught, and this value is minus of v naught. This waveform belongs to VL. So we can do the volt second balance. So the overall positive area is okay. This I will erase and I'll write like this to have symmetry. So this is A1, A2, A3, and this is A4. This whole is A3 and this is A4. So we have done IL, IM, VL. Now IC is nothing but IL with zero average value. So in the same waveform I'll draw IC like this. IC will be like this. First it will rise, then it is constant, then it will fall, then it is constant, then it will rise, constant, fall, constant, rise. So this is IC. And V naught is IC is dV naught by IC is C into dV naught by dt. So V naught is 1 by C integral IC dt. So integral of this function, if I draw like this, say that this waveform is V naught. So I am integrating a y equals to mx all the time. So it will be m into x square by 2, a polynomial like this, rising polynomial. Then integrating a constant term will be a linear term. It will be a straight line like this. Then it will be as the line is falling, slope is negative, it will be a falling polynomial like this. Then again it will be a constant term, it will rise like this. Then again a rising polynomial, straight line, falling polynomial, rising straight line. This is V naught. So this is the overall average value of V naught, which is nothing but is seen here, V ns into V in by Vp plus V naught. This V naught is used here. So I think secondary side is done. We have drawn the waveform of IL, VL, IC, V naught, and the load current. So I load, assumption is that I load is constant. So I load is a constant value throughout it. So I think secondary side is done. Now we'll see the secondary of the transformer, that is the diode currents. We'll draw all the diode currents D3, D4, D5 in a single graph. Then we'll come to the primary side. So we'll see the diode D3. The diode D3 in first case is on, off. We will not draw this freewheeling. We'll consider only without define. This all is considering without define. So the diode is on, off. Okay, we'll see. So that we saw that diode in first case is on, second case that is 0 0, but without D5 it is on, and in third it is off. So the voltage across the diode across case 1 and 2 is 0, and then it is what? The voltage across the in this case diode in this case is what? If this is conducting, the voltage across the diode is nothing but overall secondary voltage. So voltage across the diode is minus of 2 ns by np v in. So 0 0, again 0, then case 1 0, case 2 0, again case 2 0, case 3 this. So this waveform belongs to VD3, and the value of this term is minus 2 ns by np v in. This is the steady state rating of the diode, 2 ns by np v in. Yes. Similarly for diode D4, okay, now we'll draw the D3 current. We'll draw the current of the diode D3. In first case it is IL, in second case it is IL by 2, and in third case it is 0. IL by 2 0. So in what was the IL? This was the IL. So it is like this, IL, then IL by 2, but here IL is flat top, so it is, we'll do the just half of it. IL by 2 0. Again IL by 2 0. So this is ID3. Now we'll draw the waveform of D4 diode. We'll see if we can draw here only. Okay, we'll draw on the same thing. So voltage across diode D4, VD4. So first case it is off, so it is 2 into ns by np v. Case 1 it is diode is off, it is on, and it is on, off, on. So it is like this, off, on, then on. Only in case 1 it is off, so it is like this, and this value is again minus 2 ns by np v in. This waveform belongs to VD4. Now ID4. ID4 is 0, IL by 2, 0, IL by 2, and IL 0, IL by 2, IL, 0 IL by 2, and oh, there is some mistake with let me check the ID3. ID3 will be case 1 it is IL, yeah, case 1 it is IL, then case 2 it is IL by 2, case 3 it is 0. So IL by 2 0, IL by 2 0. Oh, here it should be, so there is some mistake in this waveform. I'll redraw it. So we'll draw ID3 again. So case 1 ID3 was IL, case 2 IL by 2, and case 3 0. IL by 2 0. Case 1 is IL by 2 0. Then case 2 it is again IL by 2. Case 1 we'll draw IL by 2 little bit bottom, say like this we'll draw, so it is like this. Then case 1 it is again IL by 2 0, and again IL by 2. So it is like this. This is ID3. Similarly, if we draw ID4, it will be 0 IL by 2 IL. Case 1 it is 0, then IL by 2, and it is IL, then IL by 2. Case 1 0 IL by 2, and in case 3 it is minus of IL, then again IL by 2. So it is like this pattern. This waveform belongs to ID4. We have drawn all the waveform of the diodes also. Then we'll go to the primary side. In primary side we have the switches. We have to, now we will plot the voltages VS1, VS2, IS1 and IS2. In first case VS1 is 0, second case VS2 is 0, and VS1 is 0, 0, and then 2 V in. Case 1 0, case 2 0, and I think it should be minus 2 V in because it's a switch. So yes, because this is plus of the switch. minus 2 V in, then again 0, then 0 0 minus 2 V in, 0 0. This is minus 2 V in, this is VS1. Then we'll draw IS1. Case 1, IS1 was what? IN, that is IM plus IL into NS by NP. In second case, the current is 0. Third case it is 0. So only one case the current is there. That is the case number 1. The current through the switch S1. That is IM plus IL into NP by NS. This plus NP by N2. So some slope 0 0 0. Positive slope 0 0 0. This is IM plus NP by NS into IL. Case 1 we have a current, case 2 we don't have current, and case 3 also we don't have current. Yes. Now for the other switch we'll draw. For switch 2, in this case it is minus 2 V in 0 0. Minus 2 V in 0 0 0. Minus 2 V in 0 0 0. This waveform belongs to VS2. IS2, IS2 here is 0 0, and IS2 in this case is IM minus NP by NS into IL. So already IM has a negative slope, and case number 3, right? Yeah, in case number 3 IL also has a negative slope. So it will be this fashion only in case number 3. So it will be like this. I'll use some other color. I'll use this dark blue color, and in case number 3 so 2, then 1 2 and again 3. The value of this slope is IM minus NP by NS into IL, or NP by NS into IL is IL dash, and this waveform belongs to IS2. So we have drawn all the waveform of the all the steady state waveform of the push-pull converter. Now we'll quickly do the volt second and amp second balance. In volt second balance, we have to see the inductor current. So A1, A2, A3, A4. So A2 is equals to A3. So A1 equals to 2A2 plus A3. A1 equals to A2 plus A3 plus A4. this time is D into T switching by 2. Why? Because this is T switching and this is T switching by 2. This whole is T switching by, and this is whole is T switching. Yeah, this whole is T switching. So the switch is on for a duty ratio, so D is 0 to 0.5. So this is so for, if you want to write A1 is D into T switching by 2 into, first we'll write the value of this, Ns by Np V in plus V naught. Ns by Np V in plus V naught into what? D into T switching by 2 equals to, that is A1. What is A2? A2 is T switching by 2 minus D into T switching by 2 into what? Minus V naught. Minus V naught into T switching by 2 minus D into T switching by 2. A3. Again, this time is D into T switching by 2. Because for both the switches S1 and S2, the on time is the same, T is the same. The only thing is that the switching of S2 is delayed with respect to S1 with a time of T switching by 2. So it is minus of Ns by Np into V in plus V naught. So I'll directly write minus of Ns by Np into V plus V naught into T switching by 2, and now last is V4, A4. A4 is minus V naught into this, so minus V naught into T switching by 2 minus D into T switching by 2. So what we saw in this case is that this term and this term are identical, and this term and this term are identical. If we bring the identical terms together, it will be 2 into Ns by Np V in plus V naught into T switching by 2 equals to minus 2 V naught into, we'll take T switching by 2 outside, it will be 1 minus T. So 2 to get cancelled, T switching by 2 get cancelled. So it will be D Ns by Np V in plus D V naught equals to minus sign is there, so V naught into D minus V naught. So D into V naught get cancelled, so therefore V naught becomes D into Ns by Np into V in. This is the mod, this is the ratio between the input and output voltage, steady state. So it is D into Ns by Np, and D lies between 0 to 0.5. So this gain can be selected based on the number of turns, because the value of D, there is a limit on the value of the variation of D. Similarly, we can implement amp-second balance on it. So basically, while we equate the area, we should not take the sign of it. We have to directly equate the area. So basically, this negative will become positive, positive, positive. I'm sorry, means yeah. So this is the steady state relation of the input and output voltage. So in this case we saw that the operation of the push-pull converter in the steady state operation of push-pull converter, and also the basics of center tap transformer, how the magnetizing branch is split into two, and the operation of the push-pull converter in the three cases of the switching pattern. Then we saw that the overall flux waveform is positive as well as negative. So it occupies two quadrant of the BH curve. That is the quadrant number 1 and quadrant number 3. And we saw the operation with and without the diode D5 in the three cases, and subsequently we have drawn the waveforms and derived the volt second balance of it. So in the next lecture we will see other DC-DC isolated converters like half bridge, flyback. Thank you.